Okay, so welcome everyone to today's One Word IAMP Mathematical Physics Seminar. This is a regular event hosted by IAMP, the International Association of Mathematical Physics. And if you're watching this on YouTube and if you're new to this seminar series, please click the M intersection phi logo you see below, and then you will see our webpage. And then you will learn more about this seminar series. And please, we encourage you to join our mailing list and also to the IAMP. Okay, so today or tonight, it's our great pleasure to have Naoto Shiraishi, or Shiraishi Naoto-san, and he's going to tell us about proving non-integrability of quantum spin systems. Okay, Naoto, the floor is yours.
Okay, thank you for introducing. I'm Naoto Shiraishi at the University of Tokyo. Today, I talk about a recent result on proving quantum non-integrability of some spin systems. My talk is based on these papers, so if you're interested in, please see these papers. This is the outline of my talk. First, I'll explain the background of my research. Uh, Integral systems are one of the most important topics in mathematical physics, and various models are proven to be integrable. Integral systems are known to have several good properties. For example, their eigenenergies and eigenstates can be exactly solvable. And in addition, integral systems also known to have infinitely many local conserved quantities, in the case of a local Hamiltonian. Throughout this talk, we consider only the systems with a local interaction. However, integral systems have some several anomalous properties. For example, integral systems do not summarize, and integral systems also show anomalous transport, and the level statistics of eigenenergies are also different from the ordinary one. And it is considered that these anomalies are triggered by the presence of local conserved quantities. So it is strongly believed that generic systems are non-integrable. So non-integrability is ubiquitous. Besides the ubiquitousness, non-integrable systems are important topics, and there are many important questions on non-integrable systems. For example, if a system is given, for example, we want to study a system, then in some cases, we want to decide whether a given system is integrable or non-integrable. Of course, if this system is integrable, what we should do is just proving or solving this system. But what should we do if this system is non-integrable? Another important question is whether our knowledge of the our present knowledge of the integral system is perfect or not. So we have many a large list of integral systems, but we don't know is it the perfect list, a complete list, or there are some hidden unknown integral system which is waiting to be discovered. If we study only the integral systems, we cannot answer whether our list is complete or it is incomplete. And maybe in addition, maybe it appears slightly technical, but one important question is whether there exists some intermediate system. We have at present we have only two extremal cases. One is integral system with infinitely many local constant quantity, and the other is non-integral system which has a zero non-trivial constant quantity, and there is no intermediate one. So whether there is a intermediate system with a finite number of local constant quantities or not is also an interesting question. And these questions should be solved in a rigorous mathematical physical manner. However, unfortunately, few rigorous studies have investigated non-integrability. My guess is that one reason is Because no solution or no local conserved quantity is very uneasy to treat. Since the negative proposition is usually uneasy to treat. The most existing studies analyze by fixing a solution method. For example, fixing a method as a beta ansatz. And study or show that this model can't be solved by beta ansatz. But of course, this approach is very limited. We can't exclude the possibility that this model can't be solved by, for example, beta ansatz, but is solved by another method. Maybe this is unknown, very new method which we have not known now. So okay. Now in this talk, we characterize non-integrability by the absence of non-trivial local conserved quantity, which is one of the standard definition. And we employ this as a working definition of the non-integrability. Here, we define local conserved quantity by the conserved quantities given by a sum of spatially local quantities. And we say that this is non-trivial if the size of the support is larger than the Hamiltonians. To characterize this in a precise manner, we introduce first we introduce a k-support operator, which is operators whose support is k contiguous side. For example, this operator acts on 3 sides, but its contiguous support is 5. So in this case, this A is a 5 support operator. And using this, we define the k local conserved quantity as a conserved quantity which consists of at most k support operators. And we also require that one of k support operator has a non-zero coefficient. And we say that there is no local conserved quantity if there is no k local conserved quantity with k equal order 1. Before going to my result, we first explain one important attempt, the Grabowski-Marshall conjecture. Grabowski and Marshall conjecture that a shift invariant system with nearest neighbor interaction is non-integrable if it has no 3 local conserved quantity. They put this conjecture by examining non-integrable systems. And they also find by exhaustive search that the XYZ chain with Z magnetic field and some zigzag spin chain or next nearest neighbor interacting system have no 3 local conserved quantity. So combining this conjecture and this observation, they also conjecture that these models, XYZ chain with Z magnetic field and some zigzag spin chains, are also non-integrable. But of course, this is just a conjecture, and this is not a rigorous approach. But in this talk, we treat non-integrability in a rigorous manner, and some of their conjecture is solved in the affirmative. Now we move to our main result. First, we treat the XYZ chain with Z magnetic field. Our main result in this chapter is that our system is S equal 1/2 XYZ chain with Z magnetic field with periodic boundary condition. The Hamiltonian is given as this. This system has no non-trivial local conserved quantity if these 3 interaction coefficients Jx, Jy, Jz is non-zero and Jx is not equal to Jy and H is non-zero. If Jx equals Jy, this is the XXZ model with Z magnetic field. And if H equals 0, then this is XYZ model. And these two models are known to be integrable. So, except for non-integrable cases, this system is indeed non-integrable. This is the main claim of this theorem. So this is the first rigorous proof of non-integrability. And Grabowski-Marshall conjecture is solved in the affirmative in this model. Okay, this is the main result. And to prove this, we introduce several symbols and notions. We denote by Q a candidate of conserved quantity. we can prove that Q is shift invariant because H is shift invariant. But we accept this property without proof in this talk. So for example, Q can be written as this one. And we denote, for example, the summation of xi plus 1, yi plus 2 over site I, but simply by xxy. So, for example, a candidate of 3 local constant quantity can be expressed as this. And because any two times two Hermitian matrices can be expanded by the 3 Pauli matrices x, y, z and additive operator, so there are at most 64 terms, and this expansion is complete. So by some method, we can show that if this Q is conserved, then all the coefficients of a 3 support operator is 0. This is our theorem in the case of k equals 3. And meanwhile, we treat the case of k equals 3. And we prove this theorem. To do this, we further introduce some symbols. Let us consider this commutation relation. We here the first term xyz is operator in Q, possibly in Q, and xx is an operator in H. We denote this commutation relation as this. Here, the horizontal position means the spatial position. So this means that the x is on site I, y is on site I plus 1, z is on site I plus 2. This visualization clearly shows that the overlap of these two operators are only on site I plus 2. And the result is x, y, y, x, because the commutation of z and x is y. And if this commutation relation results in this operator x, y, y, x, in this talk we say that this commutator generates x, y, y, x. Then in the case of k equals 3, there are two commutators generating x, y, y, x. One is this one, and the other is this commutator. And we can easily show that there are only two commutators generating x, y, y, x. And we know that the coefficient of x, y, y, x in the commutator of q and h is 0, because q and h commutes. So we find that the coefficient of x, y, z and the coefficient of z, y, x should satisfy this linear relation. Usually, we by considering force support operator, then we obtain a linear relation with two coefficients. However, in some cases, there are only one commutator generating a force support operator in the commutator of Q and H. One example is XXXY. This operator is generated only by this commutator. Because no operator satisfy this commutation relation. So no operator, the commutation of no operator, an operator and x never results in x. So we have no solution in this commutator, and so xxxy is generated only by this commutator. So we find that the coefficient of xxz should be 0. Using this, we can further show that some other three support operators should have 0 coefficient. For example, we consider commutator generating yzxz. This is generated by these two commutators, and we find this linear relation. But we know that the coefficient of xxz is 0. So we find that the coefficient of yzy is also 0. And applying this type of techniques repeatedly, we finally find that the quotient of ABC is non-zero only if ABC is a permutation of x, y, z. And all other three support operators have a zero coefficient. In addition, the remaining six coefficients satisfy this linear relation. So it's sufficient to prove one of these six coefficients to be zero. This completes the proof for k equals 3. To do this, we next analyze the three support operator in commutative QH. We here consider YZY. YZY is generated by these four commutators. Two are commutators of three support and one support. Here, Z comes from the Z magnetic field in Hamiltonian. And two are commutators of two support and two support. And this is very general situation. Usually, four commutators generate a single three support operator. And this results in this linear relation. But in some cases, only three different commutators generate a three support operator. An example is YYZ. This happens because no two support operator satisfy this commutation relation. Similar things happen in the case of XXZ. In general, if the two left end or right end are the same operator, then this this operator can't be generated not the maximum numbers of commutators. And these two relations implied these two linear relations. Now we have three relations listed as this. Then you can see that there are two qxy and there are two qyx. So by multiplying proper coefficients and summing them, we can erase these two unknown coefficients. And we can obtain only the relation of three support operators. But we know that all of these coefficients are linearly connected. So inserting this relation, we have this relation. So unless h is 0, this is xyz model, or jx equals jy, this is xxz model with the magnetic field, we find that the coefficient of xyz is 0. So the absence of three support contact quantity is proven for case k equals 3. We here note that if h equals 0, the Hamiltonian is xyz model which is integrable. So this model has three local constant quantity. The expression is known written as this. But please see these six coefficients. These six coefficients is consistent with the condition obtained in step 1, this relation. So we can also understand our procedure as this. In the first step, we restrict possible local constant quantity in the form of XYZ model. This holds with and without magnetic field. And then, if there exists magnetic field, then this local constant quantity can't be conserved. And so there is no three local constant quantity. And similar things holds for general K. Now we move to our general proof for general K. We here summarize the logic flow for K equals 3. In the first step, we analyze four support operators in the commutative Q and H. And we restrict candidate of three support operators in a specific form. And most of the three support operators should have zero coefficient. And in addition, we also show that the remaining coefficient of three support operators should satisfy a linear relation. In the second step, we analyze three support operators in the commutator of Q and H and show that one of the remaining coefficients of three support operators is zero, which completes the proof. And in fact, the logic flow is very similar and almost the same as in the case of general K and the case of K equals 3. The logic flow for general K can be written as this. In the first step, we analyze K plus 1 support operator in the commutative Q and H, and we restrict the posterior form of K support operator, and show that most of the K support operators should have zero coefficient. In addition, we show that the remaining K plus 1 support the coefficient of K plus 1 support operator should satisfy a linear relation. So what we should do is to show one of the remaining coefficient is zero. And this is done in the step 2 by analyzing K support operator in Q and H. So we shall see the first step. We see an example of in the case of K equal 5. Here two two operators are connected by a linear relation by considering these commutators. But why these two operators, yddx and xddyz, are connected? What structure lies behind this? To see this, we introduce a signless product of Pauli matrices. This is a very simple rule product. Using this, we express these two operators as this. Here, we compute the product in the vertical direction. So for example, x is x, and xy is z, yx is z, xz is y, and z is z. So these these four operators xx, yy, xx, zz leads to xd, dyz. Here, we call such a operator with the same Pauli matrices as a doubling operator, so xx, yy, zz. And if an operator can be expressed by the product of doubling operator as a xd, dyz, we say that this operator is a doubling product operator. So these two are doubling product operators. Now we can see that why these two operators are connected. We connect these to yddx and xddyz by these commutators. But we can see this. These red rectangles are the same, and these black rectangles are the same, zz, and these blue rectangles are the same, yy. So by removing the yy from left and adding zz to right, then yddx becomes xddyz. This is the structure. And in general, and two operators are connected by this procedure can be understood as a connection by adding doubling product operators as the left end or right end and removing the doubling product operators from the left end or right end. We then find that if an operator is a doubling product operator, then this may have a non-zero coefficient. But if it is not, then this operator should have zero coefficient. Before going to explain why, we first check that this property holds in the case of k equals 3. The remaining 6 operators are this, and they are doubling product operator. Because, for example, yzx and yxz can be expressed as this. So they are indeed doubling product operators. Now we see why non-doubling product operator should have zero coefficient. Let us consider yzx. This is a non-doubling product operator because this is not a doubling operator. Then, by removing yy from left and adding zz to right, yzxzx is connected to xxdyz. But we know that we can easily see that the two leftmost operators are the same. So for example, by adding yy to right, we this operator can form no pair. This means that xxzyz should have zero coefficient. So yzxzx also have zero coefficient. Now we summarize step 1. In the step 1, we restrict the form of a candidate of k plus 1 support operator, or k support operator. This is a non-doubling product operator. So all the all the non-doubling product operators should have zero coefficient. I'm sorry. Maybe I'm sorry. This is a typo. This is a k, not a k plus 1, but a k. And the remaining operator, doubling product operator, should satisfy linear relation. But this is easily shown because any two doubling operator can be connected to each other by removing a doubling operator and adding doubling operator. So these two properties are indeed demonstrated in step 1. Now we move to step 2. In the case of k equals 3, in general, a 3 support operator is generated by two commutators of 3 support and 1 support, and two commutators of 2 support and 2 support. And in the case of general k, similar things hold. So a k support operator is in general generated by two commutators of k support and 1 support, and two commutators of k minus 1 support and 2 support. In the case of k equals 3, however, some 3 support operators are generated only by 3 commutators. And similar things again hold in general k. In some cases, two, only two commutators generate k support, two commutators of k support and 1 support, and one only single commutator of k minus 1 support and 2 support generate k support operator. These things may happen. This happens in this case. An example is zyzxx. Again, this is in the case of k equals 6, and this is a k support and 1 support. But in this case, we have only one commutator of 5 support and 2 support, because this commutator does not exist. So again, the reason is very similar to the previous cases. And in the case of k equals 3, we align many obtained linear relations and erase these coefficients. Here, the first two coefficients are on k support, and the remaining are k minus 1 support. And we can erase the k minus 1 support coefficients of k minus 1 support operators. These are unknown coefficients, but fortunately we can erase. And the remaining one is a relation only on coefficients of k support operators. And if this relation is non-trivial, we find that these coefficients are 0. And similar thing holds for general k. In general k, the obtained linear relations are in this form. So two coefficients of k support operators and maybe one or two k minus 1 support operators. And we can set such that these two are the same coefficient and these two are the same coefficient and blah blah blah. Then same terms are cancelled. So the question is whether such a good sequence exists or not. Unfortunately, there indeed exists. But of course, I have please do not try to understand this because there are many symbols which I have not explained. But instead, I present one example with k equal 5. In the k equal 5, we first consider commutator generating xxyzy. Because two leftmost operators are the same, there are only 3 commutators. And we next consider these commutators. Now you can see that XX, these two operators are the same. And again, these two operators are the same, and these operators are the same. So we can delete these coefficients by multiplying proper coefficients. And these the remaining coefficients are only on 5 support operators. But we know that all the 5 support operators, the expression of 5 support operators, because they are doubling product operators. And combining, I'm sorry. And you can see one interesting point that here the Z magnetic field is at the left end and Z moves from left to right. I don't know why exactly, but empirically, I know that to obtain a non-trivial relation, we should add some irregular term to the left end and then move it to the right end. Then this succeeds. Otherwise, for example, if we add a irregular term to the left end and it finally goes to return to the left end again, then the obtained relation is a trivial one, 0 equals 0. So we can extract no information on the case of operators. And in this case, we can extract a non-trivial relation as this. So again, unless H is 0 case, which is XYZ model, or Gx equals Jy, which is XXZ model with a geometric field case, then this coefficient is 0. So this this completes the proof of the absence of k local conserved quantity. Now, sorry. Now we finish the proof of the non-integrability of the XYZ chain with geometric field. So we next consider the integrability and non-integrability, the classification of integrability and non-integrability. After the proof of the the non-integrability of XYZ chain with geometric field, several models are proven to be non-integrable. Mixed field using Ising model, and next nearest neighbor Heisenberg model, and PXP model. We note that the first one and the last one are not mine, but proven by Yuya Chiba and Park and Lee. But all of these results are on specific models. We want to know we want to know more global picture. So our next goal is to classify a wide class of models into the integrable and non-integrable. We want to decide completely. And fortunately, we have such a classification theorem. Consider S equals 1/2 spin chain with inversion symmetric nearest neighbor interaction. So inversion symmetric means that the interaction coefficient of xy is equal to yx. So this is a very one of the simplest form, but a very wide class. And we can show that this model is non-integrable, except for non-integrable cases. So this is the first complete classification of integrable or non-integrable for a wide class of systems. This classification theorem confirms that there is no missing integrable models in this class. So this means that the list of integral system in our present status is in fact a complete class of integral models. There is no hidden integral models, so we never find further integral models in this class. In addition, this theorem confirms that there is no intermediate system with a finite number of local conserved quantities. And the Grabowski-Marshall conjecture is solved in the affirmative in this class. To prove this, we first apply a simple trick, global spin rotation.
Naoto, there is a
Yeah.
question from chat. It
Okay.
says integrable in the sense of Liouville, but I think you said this. So Could you just
Integrable in
repeat?
the sense of Liouville unknown. We define the integrability and non-integrability by the presence or absence of local conserved quantity. I have explained in the
Yeah.
very first
Yeah.
part of my talk.
Thank you.
Okay. Okay. Now, we first because sorry. So in the first step of my classification theorem, we apply global spin rotation and make the Hamiltonian to a simpler form. Because the interaction matrix J is real and symmetric, we can diagonalize it by an orthogonal matrix. So this general interaction matrix can be as this. And we redefine J prime and H prime as J and H for simplicity. So the standard form of our Hamiltonian can be expressed as this. And the proof of the non-integrability is qualitatively different depending on the rank of J. This is a number of non-zero term of Jx, Jy, and Jz. In fact, in the case of rank 1, the Hamiltonian is given as this. And in these two cases, this Hamiltonian is integrable, but otherwise, this Hamiltonian is non-integrable. And in the case of rank 2, the Hamiltonian is given as this. And if these two magnetic fields are 0, then this is a integrable XYZ model with Z magnetic field. But otherwise, this is non-integrable. In the case of rank 3, this is slightly complicated, but except for non-integral cases, XZ chain with Z magnetic field and XYZ model, then this Hamiltonian is non-integrable. This is our main claim of classification theorem. Before going to a proof, we first answer some questions which which you may have. First, one may consider that we should treat only the high rank case, because the high rank case includes a low rank case, Jz equals 0 as a special case. However, this guess is not true. Okay, let us recall how to prove the non-integrability in XYZ chain with Z-magnetic field. This is the case of rank 3. In this proof, we show that the coefficient of YZY is 0. This is shown as this. We first obtain this linear relation, and we also show that the coefficient of XXZ is 0. And combining these, we find that JZ QYZY is 0. And because Jz is non-zero, we find that the coefficient of YZY is 0. But if Jz is 0, then the last step doesn't work. And in fact, in the case of rank 2, Jz is 0, the coefficient of YZY might be non-zero in the consideration of step 1. We can't exclude the possibility of the non-zero coefficient in step 1. So high rank case doesn't include low rank case. You may also have an opposite type of guess. If we succeed in proving the non-integrability of the Hamiltonian in low rank case, then the high rank case is also non-integrable, because this is a perturbation of the non-integrable model. And perturbation is usually results in non-integrable. This guess is true for most of the perturbation, Jx and Jy in this case, but not all. Let us see an example. For example, this is a rank 1 Hamiltonian, and if these two are non-zero, this is non-integrable. This is mixed field Ising model. And we add these two terms with Jx equal Jy equal J. Then this is a obtained Hamiltonian. This is a rank 3 Hamiltonian. And this Hamiltonian is integrable because this is a Heisenberg chain with a magnetic field. Of course, this in most cases, the part of the Hamiltonian is non-integrable. But if you want to know whether the given system is integrable or non-integrable, definitely, absolutely, then this approach, the part of the approach is insufficient, and we should treat high rank case in a rigorous manner. The proof, we shall draw a proof outline. The proof for rank 3 and rank 2 are similar, but that for rank 1 is very different. And the proof for rank 3 is the same as that for XYZ chain with geometric field, so we skip this. We shall provide the proof for rank 2. This is a ranked Hamiltonian, and in the step 1, possible k-support operator in Q are restricted to the following four operators. X dt x, x dt y, y dt x, y dt y. And they are essentially the same as the doubling product operator of xx and yy. Because we have only two doubling operators, xx and yy, the option is only adding alternatingly. So there are not so many, but only four possible operators. And in the second step, we construct a good sequence. Because the possible k-support operator is highly limited, we have not two, but one commutators in this zone. And the two right columns are the commutators of k-1 support and 2 support. And they are fortunately very cancelled out for all ones. And these k-support operators, the coefficient of these k-support operators have already been computed. And again, the X magnetic field moves from left to right. And then using these relations, we obtain a non-trivial relation on the k-support operators. And we show that there are no, these coefficients should be 0. In the case of rank 1, the Hamiltonian is given this. I should mention that the non-integrability is proven not me, but by Yuya Chiba, my collaborator. But this is a single author of Yuya's paper. In this case, we should treat k-support operators in the form of z blah 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 w. Yeah, w is one of x or y, on z blah 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 z separately. We label z blah 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 w as a class A and z blah blah z as a class B. And in each class, we should perform step 1 and step 2. In step 1, the positive k-support operator in the form of z blah 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 w is restricted to this form. So this is a multiplication of zz term and x term. So the remaining one is zxxx blah 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 xy. And in step 2, again, we construct a good sequence. And these commutators are finally cancelled, and these are the operators whose coefficients have been computed. So, and using this, these are cancelled, and we obtain a non-trivial relation on these coefficients, and these coefficients are shown to be 0. In the case of z blah 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 z, the possible form is restricted to zxxxxz in step 1. This is very similar to the previous one. So the multiplication of zz and x. And we remark that this k-support operator is connected to k-1 support operator. Z is connected to y, x, 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 y. Because removing zz and adding x results in k-1 support operator. And again, we can construct a good sequence, and these commutators are completely cancelled, and finally, the coefficients are finally cancelled. And these commutators, their y-axis y and z-axis z, both of them are known. The coefficients have already been computed in the step 1. So we can finally obtain the fact that these coefficients are 0. This completes the proof of rank 1. Now, we explain the further development of the non-integrability proof. So, after seeing these results, you may be interested in other systems. For example, what about the higher dimensional case? What about the longer interaction case? Or what about the higher spin S=1 case? Fortunately, all of them have already been addressed. But of course, I remark that some of results are not my results. First, we consider the high-dimensional case. In the in a in a system whose dimension is larger than or equal to 2, then the XX model and Heisenberg model are proven to be non-integrable. This is a collaboration of I and the organizer Haru Tasaki. And in addition, in the higher dimensional case, the transverse Ising model is also proven to be non-integrable. This is proven by Yuya Chiba. We remark that XX model, Heisenberg model, and transverse Ising models are very simple model and is integrable in one-dimensional case. So such a simple and maybe solvable in the low dimension becomes non-integrable in high dimensional case. So we expect that there are very few integral model exist in high dimension. We next explain the classification theorem of next nearest neighbor interaction system. We here consider S equal 1/2 chain with magnetic field nearest neighbor and next nearest neighbor case. Here again, we assume the inversion symmetry, so the interaction of xy is equal to yx. Then this Hamilton system is non-integrable, except classical case. This is a classical Hamiltonian. All the terms are z. This is trivially integrable, and beta solvable case. So the next nearest neighbor interaction is zz, and the nearest neighbor interaction is xz, and the magnetic field is y. This appears apparently this is non-integrable, but this model can be mapped onto the XYZ chain by Kramers Varnier transformation. So this is integrable. And this is a paper appears on arXiv today. The proof idea is almost the same as the previous nearest neighbor case, but the proof is highly complicated. One of the reasons is that because there are two interaction matrices, next nearest neighbor and nearest neighbor, so global spin rotation can diagonalize only the first one. And in general, nearest neighbor interaction have a non-zero off-diagonal element. This makes proofs much complicated. So we just show what type of case division is needed. And each case is in some, for example, this case and this case and this case require very complicated treatment. But fortunately, we can show that all of them are non-integrable. And finally, we explained S equal 1 chain. Let us consider S equal 1 chain with a bilinear and biquadratic term. This Hamiltonian is non-integrable except for the three non-integral models as this. So except for the non-three integrable cases, this Hamiltonian is indeed non-integrable. This is not my result, but the Park and Lee and Hokkyo, Yamaguchi, and Chiba showed this very good result. And of course, there are many things to do. Our proof is at present not systematic, but we should construct a good sequence for each model. So more systematic method is inevitable. And solving the Grabowski-Marshall conjecture for wide class of system is also desired. And since there are many good results on integrable systems, the connection to, for example, Yang-Baxter equation, Bethe-Ansatz, or many other good notions or results in integrable systems is very important to clarify. This is a summary of my talk. The quantum non-integrability is rigorously proven, and we completely classify the integrability and non-integrability of S equal 1/2 quantum spin chain, this next nearest neighbor and symmetric. And in this class, there is no missing integral models, and the proof most method can be applied to more general systems. We expect. Okay. Now I finish the talk. Thank you for listening.
Thank you very much, Naoto, for this wonderful talk. And I'm amazed that you talked about all these 88 slides. Amazing. Okay, so any questions or comments? Everything is welcome. Herbert, do you have a question?
Well, okay, I don't know. Maybe I can start. I mean, so I have actually, it's a very nice talk and very interesting results. I mean, I have two questions which are sort of a little bit unrelated. And one question is, yeah, I mean, of course, for the proof, I mean, you need strictly local conserved fields. Can you soften this condition a little bit? I mean, one could think about sort of things which simply are exponentially localized, but not strictly local. I mean, so this is sort of one question. And the second question concerns whether you have tried to use the same kind of techniques for classical spin systems. I mean, spins really, let's say, sitting on the unit sphere, and then you have Poisson brackets instead of commutators. But the algebraic structure looks not so totally different. And so the question is whether you have ever tried to go in this direction.
I'm sorry, I missed the first question. What question is
It was about quasi-local conserved quantity.
quasi-local conserved quantity? This is very hard to treat. Our recent paper collaborated with Harutasaki to treat slight provide a very limited result. I'm sorry. In this paper, we show that some very limited forms of quasi-local constant quantity is excluded, but in general, it is very hard because in my proof, the support, the limited support is very essential. So at present, I do not have a good idea to extend our results to quasi-local constant quantity. This is a very challenging but important problem. And the second question is on the classical extension. I haven't tried this approach. This is because I haven't considered this. This is a straightforward extension, or maybe there are many difficulties. I can say nothing. I'm sorry.
Okay, thank you very much.
Thank you.
Any other questions, comments?
I have a question whether one could use some methods to, for example, for a Hubbard model.
Hubbard.
What could you say about the approach to prove something for something like a Hubbard model?
Hubbard model. I haven't, but I heard that some my PhD student tried to do particle system, the boson system, the fermion system. So I think using this type of idea, then the Hubbard or this type of particle system can also be treated in a similar manner. So I think it is very hopeful.
Okay, thank you.
So there is a question from chat, but I think it says here the integrability means lax pair exists for a Hamiltonian system. Thanks, but so is this for classical or quantum?
Integrability means lax pair exists for quantum system.
So for classical, okay. Oh, Kolya, you're here. For classical.
For classical.
So is this a question to Herbert Schwung or what?
No. I had the similar question. I mean, I was restricting to sort of continuous spin on the sphere, but of course you can take also a classical lattice systems, for instance, and then ask exactly the same question of what you are asking. And it's not, it's not even clear whether there is a precise conjecture.
Okay, so
I also ask a question.
sure.
So thanks for a nice talk. I wonder what you consider here is all the Hamiltonian with nearest neighbor interactions or some short range interactions. But another example we know is Haldane-Shastri model, which is 1 over r squared interacting Hamiltonian. And this is also a kind of well-known integrable models which behave like free fermions. But in these cases, sometimes like Yangian operators are a conserved operators, which doesn't seems to be like proven with your idea. So do you have any ideas to include such Haldane-Shastri model like in
So you're asking some long-range interacting models.
Yes.
In the long-range interacting case, first the definition of the non-integrability is slightly problematic because if of course our definition works only for local Hamiltonian, and since if the interaction is long range, so what type? Of course, we I think there must exist some notion of integrability and non-integrability, but what type of conserved quantity is acceptable and what type of conserved quantity is rejected is highly problematic. So this pro if so I think we should first solve this type of definition problem. Otherwise, our work never works.
Okay, so any other questions, comments?
Can I ask
have a
one?
question.
Oh,
Sorry, go ahead.
Okay, I was wondering, is there any analogy between what you're doing and this very old work on integrability of classical field theories? So there are papers by people like Buller and Dodd where they try to do a systematic look for conservation laws. And then they sort of recover Sine-Gordon and, well, something that's sometimes called the Buller-Dodd model, just by looking for systematically for conservation laws in the classical context.
But I'm not familiar with this kind of classical field theory, and I heard that several Hamilton system, the list of all Hamilton systems that exist for example, Zigrin's some lemma or this kind of things, but I don't- I do not use this type of analogy, and maybe some exist, but I'm sorry, I can't say anything on this relation or connections. I'm sorry.
Okay, thank you.
Can I
So
ask a question?
Oh, Kolya, yes, please.
Yes. So I'm just wondering if there is any kind of algebraic framework for this investigation of commutativity of local integrals. Something like, usually for the existence or non-existence of something, there are cohomological abstractions. Maybe there is some kind of natural algebraic setting here. Did you try to investigate this?
I'm seeing some algebraic structure. Asking. It is very interesting. The algebraic characterization is also interesting if there indeed exists. Of course, in integrable cases, there are quantum groups or this kind of things. So I'm not familiar with algebra, so I haven't explored this direction. But maybe there are good characterization. Then all the model integrable and non-integrable is completely treated in a unified way. This is a miracle, and that it is design very good, marvelous results. I hope.
Okay.
But I'm sorry, I haven't investigated.
Okay.
Kolya, do you have an idea?
No. I was thinking about these things, back in the 80s, but from the point of view of Yang-Baxter equation. But yeah, it would be very nice
Yes,
to have it.
yeah. Was a very nice point. Any other question, comments?
Maybe can I ask one?
Sure.
There is a difference between dimension 1 and high dimensions.
Yeah.
Is it possible to also look at like a chain, but with a few extra sides? And do you
yeah, in fact,
so you would lose integrability as soon as you add
in
few
fact,
sides, or?
yeah, in fact, should one-dimensional case is sufficient to prove non-integrability for wider class. In fact, what we do in a two-dimensional case is that in the first step, we restrict all the possible k-support operators, in fact, doubling product in one dimension. And then we do that adding the xx term in a vertical direction. This xx works as a single, as if a single x in the case of one-dimensional case. So in fact, only the two sides in the vertical direction suffices to show the non-integrability. So
I see.
only a very should one-dimensional this all just a ladder is turned out to be non-integrable. Although the one-dimensional is integrable.
Even worse than that, just a single chain, I mean, a chain with a single extra side.
Single extra side. Okay. So, for example, just one additional. I don't know, but this is essentially the one dimension. Essentially one-dimensional. So, except for single one, I don't know. It appears that for almost all positions, the local constant quantity is still commute. So, it appears harmless, but
So you do you need a graph with a loop?
graph?
Like a tree would not work.
I don't.
But probably this trick works. Don't you think so?
This works. So you hard consider that this is non-integrable. But yeah, to solving is very even adding a single side destroys the conventional approach. So it appears no it appears no it appears no integrable. I was convinced by her, but
looks like.
Looks like, but how to prove this is I should consider that. At present, I cannot. At present, I can't write down the proof now, but maybe it is not so hard. Just a homework level, maybe. Okay, maybe it is not easy.
Okay, thank you. Yeah.
Thank you.
Any other questions? Can I ask one?
Yeah.
So you have this complete classification. So sometimes your proof of non-integrability works, and sometimes it does not work, and then you find that it's an integrable model.
Yeah.
But but there are many different kinds of integrable models, right? Some of are very easy. They map to the models are mapped to free fermion. Some of them are very hard, and you have to use very sophisticated beta and that type of thing. And do you see this difference from your approach? So do you see from your approach how badly your method fails? Like
method, how to find?
Yeah, do you see the difference? Do you see the difference between these easily integrable models and very sophisticated integrable models?
So you are asking two integrable cases?
Yes. In integral cases, your method fails, right?
Method fail, but
does it simply fail?
Simply fails, and because a simple integrable model is usually a special type of a hard integrable one. For example, the XX chain is a special type of XYZ chain. So I usually do not treat the XXZ chain directly. So I don't know. Maybe, of course, it maybe my approach can be used to find a new integral model. This is a very wonderful one. In fact, I mean, this is different from your question, but in fact, this beta solvable case is what I don't know that this mapping, and I first find that this I cannot solve this, and then I succeed in write down the local four local constant quantities. So I'm sure that this should be solvable, and then I ask some colleagues, and I learned that this is that can be mapped to
Okay.
non-XYZ model. So this is not this is not a new integral model.
Mhm.
But then maybe this is an easy one. I don't know. But I can't find out the difference between the easy and uneasy case. But maybe higher spin case, this type of difference happens, but I haven't treated higher spin case.
Okay, yeah, thank you very much. So, any other questions or comments? It's late.
Then let me maybe ask a question, if I still may. Maybe it was answered already in a different context, but I'm wondering if it would be possible to generalize it to quantum fields on a lattice. So if the sigma matrices are instead creation and annihilation operators, which which sit on the lattice sides. Is there any hope for this?
I'm sorry, I haven't considered this type of reason. Maybe I don't know this type of research field even. I'm sorry. So I'm sorry.
Yeah, well, for example, there are kind of old hand-wavy conjectures that Young Mills should be integrable in some sense. So that's why I started wondering if maybe by this approach one could exclude it once and for all.
I'm sorry, I haven't considered this, so I'm sorry, I'm not sure.
Okay, yeah, probably it's too far from the topic of your talk.
Probably hard.
Thank you.
Any other questions or comments? Okay, so because anyway, the speaker and the chair are in Wednesday already, so probably it's a good time to say good night and close this session. So thank you very much, Naoto, for wonderful talk, and thank you very much, everybody, for joining us.
Bye.